Check it out now, y'all.
nanoHUB-U, online instruction.
Okay, today we start week 4 of nanoscale transistors. So last week we talked about the ballistic MOSFET, and we learned that 3,5 field effect transistors operate fairly close to the ballistic limit. But modern silicon MOSFETs are roughly 50 or 60% of the ballistic limit. And to understand why and how those devices operate, we need to talk about carrier scattering and transmission. So this week is going to be organized much like last week was. We'll begin with a couple of lectures. Today's lecture is on the physics of scattering. The second lecture is on transmission. Then we'll apply these ideas to the MOSFET and see how scattering plays out in modern MOSFETs. And then the final 2 lectures this week will apply the model that we developed to relate it to the traditional model and to relate it to experimental results on recent devices. Okay, so let's dive in. So just by way of review, let me remind you what we mean by ballistic MOSFETs, ballistic transport. For ballistic transport, we're thinking of a device that is short compared to a mean free path, or the distance between scattering events. Electrons essentially are injected from the source. They zip across the device, enter the drain, where they experience, well, first of all, they gain significant kinetic energy while they are accelerating across the device. Then they enter the drain with that kinetic energy. They encounter significant scattering, rapidly lose it, and thermalize into an equilibrium Fermi-Dirac distribution in the drain. So that's the picture we have of ballistic transport in a MOSFET. What about diffusive transport? This is just the opposite case. The channel length is many mean free paths long, so there's almost no chance that an electron will get all the way across the channel. It'll scatter many times in diffusive transport, and it may lose energy, it may scatter elastically and just change direction. It'll undergo some kind of random walk. It might return to the source and not contribute any drain current, or it might exit the drain with some amount of kinetic energy. And then it rapidly thermalizes again. So these are the 2 mental pictures that we have in these limits. I've shown you these simulation results from the IBM Damocles program several times. This is a snapshot of each electron inside a 40 nanometer channel length MOSFET simulated by a computer. You can see these electrons streaming across from source to drain, gaining a lot of kinetic energy. But they've lost some of it. There's some spread in the energy. This we would call quasi-ballistic transport. And it's very complicated. It involves a non-local dependence on the electric field and involves strong velocity overshoot. And it's a very detailed and involved problem in transport theory. We're going to try to understand this problem. Try to understand the essential physical concepts and do it in a way that we can get the ideas and we can model them in a simple but still physically sound way. Okay, so modern day MOSFETs, nanoscale MOSFETs, they're neither fully ballistic nor are they fully diffusive. They operate in this in-between regime where things can get complicated. And our goal is to understand what's going on and to do it in a way that is simple but makes physical sense. Okay. All right, we're going to be applying this Landauer approach. Last week, we assumed ballistic transport, and we let the transmission equal 1. This week, we want to talk about what happens when there's scattering and the transmission is less than 1. So we won't be talking about the diffusive limit, which is the traditional limit where MOSFET theory was worked on. We won't be talking about the ballistic limit, which is what we discussed last week. We'll be talking about the in-between regime where modern-day silicon MOSFETs operate. Okay, so let's think about current transmission just a little bit. Let's say we have injected a stream of electrons. I'll call that I of E. It's just an electron flux. You know, there's I'm not multiplying by Q, so I'm just using that symbol for the electron flux. A stream of electrons is injected. Some fraction of them come out to drain. I'll call that fraction T sub 1, 2, the transmission from contact 1 to contact 2 at this particular energy E. Now, if I don't have any electrons recombining in the channel of a MOSFET, and that's the typical case, then the electrons that don't transmit must have backscattered and returned to the source. I'll call that R sub 1,1. Injected from contact 1 and returned to contact 1. And conservation of electrons just says R sub 1,1 is 1 minus T sub 1,2. Now I could do the injection from the drain, and I would have a transmission T sub 2,1, which tells me the probability that electrons will transmit from contact 2 to contact 1 at this energy. And they might also backscatter, and again, conservation of particles would apply in that case as well. Okay, now, what happens if the electrons that are injected do not change energy while they're crossing the device? We call that elastic scattering. And that can happen either left or to the right. And a very simple thing happens in this case. One can show, actually a Fermi's golden rule calculation will show you this, that the transmission at any given energy from contact 1 to contact 2 is precisely equal to the transmission from contact 2 to contact 1 at this particular energy channel that we're focusing on, in the presence of elastic scattering. So that's a very, very powerful relation that simplifies the mathematics quite a lot. Okay, now what do we mean by inelastic scattering? What we mean by inelastic scattering is an electron injected with energy E, some fraction of it might be transmitted across in the same energy channel, but we might have some portions of that injected flux coming out in other energy channels. So we could either lose energy by emitting lattice vibrations, gain energy by absorbing lattice vibrations. So there's some vertical flow of electrons in energy space here as well. Under these conditions, the device is not reciprocal. Transmission from contact 1 to contact 2 does not equal the inverse T sub 2,1. So inelastic scattering in the device is much more difficult to treat rigorously. Now in practice, we can get by with some approximations. If we look in the linear regime, we have a small drain bias. And then, even if there's a little bit of inelastic scattering in the channel, things are symmetrical because the drain bias that's been applied is so small the device looks the same from both directions. So under those conditions, it's not bad to assume that T sub 1,2 is equal to T sub 2,1. Under large drain bias, we can have electrons transmitting from contact 1 to 2, but this very high electric field and barrier at the drain will make it very difficult for electrons to transmit from contact 2 to contact 1. So in that case, we only have one transmission to worry about, and the fact that the two aren't equal won't be too much of a complicating factor for us. So in practice, we're going to be able to get by with just one transmission. All right? It's not obvious, so I wanted to take a little bit of time to discuss that. How we can get by with using simply one transmission for going in both directions. But it's a reasonably good approximation for us here. Okay. Now, we've seen already, I've given you an expression for the transmission in terms of the mean free path, and we've seen that the transmission depends on the average distance between scattering events. We're going to want to understand that in a little more detail. The mean free path is the product of the electron velocity times the time between scattering events. The electron velocity comes from the band structure. The scattering time comes from the band structure and the scattering physics. So let's talk for the remainder of this lecture, let's try to get a simple understanding of scattering. Since the velocity is relatively easy, it comes directly from the band structure. So in thinking about scattering, we can think about it this way. Let's do a conceptual experiment. Let's say that we inject a stream of electrons with some particular momentum and energy. Let's say the momentum is directed along one direction and the electrons have a lot of excess kinetic energy. We inject them at time t equals 0 into a semiconductor and we ask what will happen. Well, if we wait a time tau, which is sometimes called the single particle lifetime, it's how long the electrons live in that particular state before they scatter, then we'll find that after that lifetime tau, most electrons have on average scattered. The initial direction may not be completely randomized yet. The initial energy may not have relaxed down to the lattice energy, but every electron has, on average, experienced one scattering event. Now, if I wait a little bit longer, a time that we would call tau sub m, the momentum relaxation time, then on average, we've relaxed all of the momentum. Now there's no net momentum or velocity in any given direction. But the electron still may have considerable amount of kinetic energy. So you can see that the momentum relaxation time is greater than or equal to this average time, depending on the details of the scattering events. Now, if I wait even longer, the electrons will dissipate their kinetic energy. The length of the arrows is an indication of the kinetic energy. The electrons will come into equilibrium with the lattice. We call that the energy relaxation time. And you can sort of see that the energy relaxation time should be even greater because it takes longer to shed that excess kinetic energy. Now, how does one compute these times? We're not going to get into the details of computing these times in this course, but I want to give you a feel for how it's done so that you can appreciate some of the general results. The basic quantity that we're interested in is this transition rate from one momentum state to another momentum state. So S of P to P prime is the probability per unit time that an electron coming in with momentum P, when it encounters some type of random scattering potential, the probability that it is deflected into another state P prime. That's what we call the transition rate. So that's the microscopic process that goes on. If I want the 1 over the average particle lifetime, this is what we call the scattering rate. This is the probability per second that an electron will scatter somewhere to any P prime. Then I simply have to sum the transition rates. The electron comes in with momentum P, it can scatter to some momentum P prime, and I have to sum over all of those states that the electron can scatter to. If I want to compute the momentum relaxation time, then I have to weight each of those transitions by the change in the momentum along some coordinate axes. If the scattering event is anisotropic and it just deflects the electron by a small amount, and some mechanisms are that way, like charged impurity scattering, then there won't be much momentum relaxation or change in momentum, and the momentum relaxation rate can get very long. It means it might take many collisions in order to randomize the momentum. Now, if I want the energy relaxation rate, I do the same thing. I take the transition rate from P to P prime, I weight it by the fractional change in energy that occurs during that process, and then I sum over all of the final states that the electron can scatter to. And this gives me the average energy relaxation time, or 1 over that is the energy relaxation rate for this electron that is coming in at some momentum P with some energy E. Okay. Now, how do we actually calculate that transition rate? Because once we have the transition rate, we can get the characteristic times, and those have a clear physical interpretation. Well, we do it by perturbation theory, using a simple technique that's introduced usually in the first course in quantum mechanics, called Fermi's golden rule. The idea is that we first have to identify what the scattering potential is. Once we have the scattering potential, then we take the wave function of the electron as it's entering, and the wave function of the final state that it gets scattered to. The scattering potential varies strongly on the wavelength of the electron, so we have to do this quantum mechanically. And the prescription is known as Fermi's golden rule, and I'll just state the result. Some of the references derive this result. If you've had a course in quantum mechanics, you've probably seen and used it. But the transition rate from P to P prime is 2 pi over h bar, magnitude squared of a matrix element, times an delta function which expresses energy conservation. The matrix element, notice that the order here is switched. The initial state is second, the final state is first. We simply take the scattering potential that we've identified, sandwich it between the wave function of the initial state, the wave function of the final state, perform that integral, take the squared magnitude, and we've got the transition rate for that particular scattering process. This delta function says that the final energy is the initial energy plus the change in energy that occurred during the scattering event. If this is a static potential, like just a charged impurity, then it's an elastic scattering event and there's no change in energy, just in direction. That's what we call elastic scattering. If this random potential that we're dealing with is maybe due to a lattice vibration, then we can either absorb energy h bar omega from the lattice, or we can emit energy h bar omega from the lattice, and we have an inelastic scattering event. And we've scattered either to a higher or lower energy. Now, this is a very simple, probably the simplest way to treat scattering in quantum mechanics, but it's the one that's most widely used for semiconductor problems, and it generally works pretty well. There are some assumptions. One is that the scattering is very weak, so most of the electrons go through and don't get scattered. And one is that it occurs infrequently, so that we can wait a long time between scattering events. And that's needed because we have this uncertainty type relation between the uncertainty in the energy and the time. If the time between scattering events is long, then the uncertainty in energy is small and energy conservation applies. So we need a long time between scattering events for energy conservation to apply. Let's do one simple example, just show you how this works. Let's take a plane wave in a three-dimensional bulk semiconductor as the incident electron. Let's take a plane wave as the scattered electron. There should be a block function with a periodicity of the lattice that will introduce some numerical details that we worry about when we do detailed calculations, but we don't need to worry about here. Let me assume that this scattering potential is a very sharply peaked short-range potential. Let's just take it as a delta function, some constant times a delta function located at the origin. And then let's calculate the transition rate. So if I calculate my matrix element, the delta function makes it easy to do, and we will simply get a constant divided by the volume. That means I can plug that into my matrix element squared, and we find that the transition rate is proportional to some constants times a delta function, which says that the scattered energy is equal to the initial energy. Okay, so for that short-range potential, we get a simple description of the transition rate from P to P prime. If we want the scattering rate, we have to sum over all the final states. I have a little arrow up there, which is intended to remind me that we have a spin degeneracy of 2. So each of the final states has a spin up and spin down location. But if this scattering mechanism is not a magnetic one, if it doesn't affect the spin of the electron, then I can only sum over the spin states that are parallel to the incident electron. So only over half of the states. Now when you do that sum, you can sort of see what we're doing is we're going through every state in the Brillouin zone, and we're asking, is the energy of that state equal to the energy that I'm looking at? If it is, we get a contribution. So we're basically adding up all of the states at this particular energy. Then we're dividing by unit volume. So this is a way, this is actually a definition of the density of states at that energy. And the factor of 2 is just because we're only looking at the states that have spin parallel to the incident electron. So the final conclusion is something that we could have probably intuited. The probability of scattering per unit second is equal to the density of final states at the energy of the final scattered electron. So that just makes sense because the more states there are to scatter to, there's some probability of scattering to each one. So there are some scattering mechanisms that are anisotropic and pick out preferred states, but for the simplest scattering mechanisms, we simply scatter with equal probability to all of those states so that the total scattering rate is proportional to the density of states at that energy. So that's a very simple way of looking at scattering that works very well frequently. So for elastic states, an electron that comes in at an energy E, the scattering rate is proportional to the density of states at energy E. For phonon absorption, an electron comes in at energy E, absorbs energy from a lattice vibration, so the scattering rate is proportional to the density of states at energy, incident energy plus h bar omega. And if we emit a lattice vibration or a phonon, and that's the scattering event, then the scattering rate is proportional to the density of states at the incident energy minus a little bit. Okay. So that's a simple way to look at transmission, and we've discussed the physics of scattering in a very quick way without going into a lot of details, but I just want to give you a feel for how these calculations proceed. You know, if we need to do them, we could go into the details, and you could do that later when you need to. But the goal for this lecture was to give us a physical feel for what goes into the calculation of those scattering times. The velocity comes from the band structure, and that means we can compute the mean free path. Our next task is going to be to dive in a little more deeply into this notion of transmission, because transmission is central to our view of transport, and we'll take up and continue the discussion on that topic in lecture 2. Thank you.